I think when I started this session, it said it was recording. All right, I left this up on purpose so that everybody could copy down the URL if you need it. Everything and more that I wrote up for those lectures is uploaded to that website. It should forward you to a Google Drive folder and you can just pull it down. I probably won't be able to show everything that I wrote down. I got a little bit ambitious in what I wrote down. First of all, don't let my sort of antagonism in the morning discount what Francesca was telling you earlier. It's very important to understand what the thermodynamic limit is before you then start asking the question of what the non-equilibrium deviations from that are. So I think as he said, it's a sort of complementary picture. And the question that I've been focusing on, I guess, for probably 20 years now was to what degree is the quark gluon plasma in thermal equilibrium and how fast does it thermalize, and what are the necessary ingredients to apply things like hydrodynamics and kinetic theory and all this stuff to modeling the quark gluon plasma itself. And the plan for these lectures is that today I'm going to start with some slides which are basically to motivate you, like why should you still pay attention for 8 hours? In the first pass, you'll see some of the same slides on, I think, Friday or whenever my last lecture is. I won't necessarily explain everything on the slides today. The goal is to show you the things I'm going to explain to you over the course of the lecture series. But it's to give you a feel for it so that you know where we're going. So you can consider the first slides as a sort of outline of what you're going to see. So many of you may be familiar with the QCD phase diagram. If not, you're going to see it again. This is my very plain version of it. Here is the temperature axis. Here's the baryochemical potential axis. Over here exist interesting things like neutron stars, supernova, neutron star mergers. But what I've been primarily focused on is the physics of high energy heavy ion collisions, which basically live right here on this axis where mu b is equal to 0 and generate initial temperatures on the order of 600 MeV at LHC energies, and then you sort of make a transition in this way through what's called a crossover phase transition, which I drew here as a dashed line. A crossover phase transition is one that's infinitely smooth. You can take as many derivatives of the order parameter as you like, and there's no discontinuities. That crossover line is supposed to end in a second order critical endpoint. Nobody knows where that is or even if it exists. In fact, this is the search for this critical endpoint here was the reason the US government spent, I don't know, hundreds of millions of dollars to continue RIC running it at lower energies rather than higher energies, because as you lower the beam energy, you move out this way in the phase diagram. All indication, this plot that I made is rather dated. I think I made it 13 years ago, and all the indications are that critical endpoint might be hiding over here somewhere. But nobody really knows. I would say where I drew it in this cartoon is ruled out by now. Now, once you get past that second order phase transition point, it becomes first order. Again, it might be a crossover all the way down. Nobody knows. That's your job as the future physicist studying this topic, is to help us figure out the details of this part of the phase diagram. This part of the phase diagram, if we just focus our attention on mu b is equal to 0 or very close to 0, it's very well understood, and we have a very good understanding of what this crossover phase transition temperature is here. There's a little bit of uncertainty here because if something is a crossover, it's smooth. You can't say something is discontinuous and you go from one phase to another. You have to define some sort of peak and some susceptibility or something in order to say where this is. But based on the standard accepted lattice measurements, this phase transition is at around 154 MeV. Now, when I entered this field as a graduate student in 1992, this was all theory. There were even no experiments. Right? Everybody was like, oh, you have a QCD Lagrangian, there should be this phase transition. And now, some 30 years later, we now do this over and over again in the lab, a million times a second. So there's been amazing advances in the field. One of the advances that occurred along this line here was the ability to measure the equation of state using lattice QCD, and if I can manage to get it on the right, if there's a delay. This is a plot of the pressure measured in lattice QCD, scaled by an ideal gas of quarks and gluons. In an infinite temperature system, this should go to 1, which is the Stefan-Boltzmann limit. This is the sort of phenomenological range of temperatures that we're dealing with these days. This is where RIC initial collisions are. This is where LHC, the first LHC energy was, and this is where the highest LHC energies are. The red points are actual lattice data, and the points are their continuum points here with the arrow bars are their continuum extrapolated results in full QCD 2+1 flavors. Then I've drawn two theory curves on here for you. In addition to the numerical extractions, there's this orange curve. This is if you just assume that whatever's going on is just a gas of hadrons and resonances of hadrons. You can just make an equation of state by just summing up a bunch of hadrons, every hadron you know from the PDG, and then maybe some more, and you get the orange line. And you can see that after around this, let's call it 175, it strongly deviates from the lattice result, which saturates. The other line on this plot is a perturbative calculation, which is the black line here, which was obtained by myself and collaborators back in about a decade ago by summing up to 3-loop order a highly complicated class of resum diagrams. That's not what this lecture is about, but suffice to say, this up here looks like quark-gluon plasma, and down here it looks like hadron resonance gas, and there's clearly a transition between the two. And if we're sitting at highest LHC energies, we're sitting up here at temperatures and corresponding energy densities that are well within the quark-gluon plasma regime. So that's why I say, we have a pretty good understanding of what's going along here. Now, since that paper was released 10 years ago, lattice people have slowly moved out in the finite mu-b axis because they have to do a Taylor expansion around mu-b is equal to 0 because of the sign problem, or use some imaginary chemical potentials. And analytically, we've also been able to go out in this direction. But my focus will be today on strictly mu-b is equal to 0. Now, as I mentioned, there's experiments going on. RIC collides gold nuclei on gold nuclei at 200 GeV per nucleon. Remember, there's 200 nucleons in each of these nuclei, roughly speaking. So this is a 40 TeV collision. It's the highest energy collisions ever. Don't tell your high energy friends that, but it is. We're taking two nuclei and we're concentrating an incredible amount of energy into a volume of space which transversely is about 10 to the minus 14 meters across. So the energy densities that you get in here well exceed 1 GeV per cubic Fermi, going up to 10 GeV per cubic Fermi. And at those super high energy densities, describing this in terms of a hadron system, it just doesn't make any sense. Now, LHC upped the game by order of magnitude, going up to 2.76 and then 5 TeV, and I've tried to indicate the initial temperatures that were reached there on this slide. And as I mentioned, RIC, the beam energy scan is actually lowering the beam energy to move out into the finite mu-b direction, and there are future experiments planned at FAIR and NICO where they'll continue to probe that part of the phase diagram. Now, the thing that's challenging about quark-gluon plasma physics is the incredibly small size of it, but also the fact that the entire event, from the time these two nuclei, these are two nuclear pancakes that have been Lorentz contracted along their direction of motion, until when they freeze out into a gas of hot hadrons, it lasts about 3 times 10 to the minus 23 seconds. And I think by anybody's standards, that's a very short amount of time. We can't really send a probe in there to see what's going on, so we have to have some sort of self-analyzing method to say yes or no, did we create a quark-gluon plasma? And that was the basic question, which even 30 years ago, we didn't know the answer to. There was a theory prediction that said, yeah, there should be this quark-gluon plasma, but then the question is, how experimentally do we prove that there is a quark-gluon plasma? Now, the little animation that's running on a loop here was generated by Bjorn Schenke, who was a graduate student of Frankfurt of mine many years ago. It's output from an actual hydrodynamic simulation. On the right is what an experimental display looks like, right? So our job as theorists is to take the out channel and then say what came over here, right? So we have to be able to analyze tens of thousands of particles, hadrons on the outgoing side and figure out what's going on. Now, in the morning lecture, you saw that it's we very frequently talk about a space-time diagram. We have one nucleus going to the left, one nucleus going to the right. They collide here at some interaction point in the limit of super high energies. This is really a point, but if it's not, infinite energy, this is blurred out a little bit, but I'm gonna take the limit because I'm a physicist. And right after they collide is when you generate the highest energy density little blob of matter in space. That's the red zone here. And this is the realm of something called colored glass condensate, or glasma. This is when you're sort of liberating a bunch of gluons from the nuclear wave function. Those gluons will then pair produce quark and antiquark pairs, such that the whole system remains at mu b is equal to 0. All of the baryons, the quarks, basically go flying down the beam pipe in these two projectiles. Now, this is not just theory. They can test where the baryon number went by putting detectors around the forward part of the collision, not around the center, but very forward down the pipe over here, and then see where the baryon number went, and they see that it went out at forward. It doesn't stay here in the central detector. So this matter that's generated here initially was only gluons to first approximation, to a very good first approximation. And then all of the quarks and all the hadrons that came out of that subsequently were pair produced. Now when I'm giving public lectures about this, what I like to emphasize is that we're turning energy into matter. It's great, right? Normally they like to run matter into energy in terms of nuclear explosions, and we do the opposite. If you were to weigh all this stuff in the end, you would find that it weighs more than what you put in. All right, oops, went forward too fast. So, this is the highest energy density right after the two Lorentz contracted nuclei have passed through one another. This might be at 0.1 Fermi over C after they pass through one another. And then as it expands, it cools down, and it eventually will start expanding transversely as well as longitudinally along the beamline direction. And both the longitudinal expansion and the transverse expansion will cause the system to cool, just like any gas expanding will cool down. In this picture, in the space-time picture, you don't have any idea of the transverse dynamics. That's why I showed you this little inset over here. The temperature is indicated in these colors here. Red is hot, orange is less hot, and then this is even less hot. Eventually, it reaches this point where you cross back into to the hadron phase. That turns out these timescales that are here on the left are from RIC collisions. So that happens fairly quickly in a RIC collision, and you only have about 5 Fermi over C before it becomes hadrons again. And then these hadrons can continue bumping into one another for a little while, but eventually they become so dilute that they don't run into each other any longer. And then they just free stream to the detector, and that's what the experimentalists observe. And then they collect those. That was that spaghetti mess that I showed you on the previous slide. Now, it used to be 13 years ago or so that it was believed that there was no period of non-equilibrium or even near equilibrium physics, that basically at 0.6 Fermi over C, which is basically a little bit after this little picture of the cartoon here, that it was become perfectly thermal. And there was a sort of challenge laid out in the field, like how could you thermalize matter in 10 to the minus 24 seconds? And there were there were 3 answers. One was you needed infinitely strong coupling, and that answer came from the ADS-CFT camp. So they said, oh, we just need an infinitely strong coupling, and I can instantly isotropize and thermalize the matter. That turned out to be wrong. So if you go and you actually solve Einstein's equations in 5 dimensions in this kind of rapidly expanding environment, you find it doesn't thermalize at 0.6 Fermi over C. I was working from the perturbative QCD side. The answer at 13 years ago was that it would be roughly within 10% of thermal equilibrium at about 2 Fermi over C. But because of that reason, perturbation theory fell out of favor because they wanted it to be thermalized down here and it wasn't. But because of these ADS-CFT studies where they showed that even when G was infinity, you couldn't thermalize this matter, people started to say, well, maybe we didn't need thermalization in the first place. So a sort of sea change occurred that we don't need to thermalize the matter, and so we don't need to assume that it's, a perfect fluid, and that's when the era of viscous hydrodynamics began. And the moment that you have a finite viscosity in the plasma, it's associated with a sort of finite relaxation time for non-equilibrium deviations. And as we'll find out over the course of the lecture, that's when you start doing nice things physics-wise, like restoring causality to the equations and stuff like that. Now, turns out that the largest deviations from equilibrium that you see here in the red and orange regions are due to some quite basic physics. And that is during this sort of the first 3 Fermis over C, that's the time period roughly before the transverse expansion kicks in here. So I can just draw it as a little tube expanding. You can think of the quark-gluon plasma as a tiny one-dimensional universe that's only expanding along the longitudinal direction in space. And as we know from cosmology, if I have an expanding universe, things get redshifted, right? So momentum get reduced. The wavelengths get increased, momenta go like 1 over the wavelengths. So this little cartoon will quickly convince you that if it's not transversely expanding, but only longitudinally expanding, the longitudinal momentum will be depleted, the transverse momentum will remain constant. And kinetically, we know that pressures are related to kinetic energies, right? So if I have more momentum in this direction rather than the transverse direction than in the longitudinal direction, I'll have more pressure in the transverse direction than I do in the longitudinal direction. Now, eventually, this doesn't continue forever. It would continue forever like this if there was no interactions between the quarks and the gluons. So I've tried to summarize what we knew, and this cartoon is actually from 2006, so it's now quite old, but I didn't have to change it since then, which is great. If you plot the longitudinal pressure in the local rest frame of any fluid cell here in the plasma divided by the transverse pressure, what you find is it doesn't matter what initial, you can say it's in perfect thermal equilibrium and an isotropy so that these two things are equal, but because of this rapid expansion, it gets drawn down to a phase where it's highly anisotropic in momentum space. Now, I even drew some other limit down here where the longitudinal pressure is negative, and that was a prediction coming out of the colored glass condensate. Now, you might ask, with a system of particles, how do you get a negative pressure? Well, you can't. But with fields around, you can. And in the colored glass condensate, there's very coherent color fields, and you can generate negative pressures from coherent color fields. Actually, you can generate a negative pressure from a coherent electromagnetic field. If you were sitting on top of a bar magnet right on the North Pole, and you were to measure T mu nu right out of Jackson, you would find that there's a negative pressure there right on the top of it. Does it mean that space is unstable? Of course not. It's just, you can't think of it in a particle manner. But anyway, even if you start with this negative pressure CGC, you find that you also get drawn up into this phase very quickly, and that has to do with something called plasma instabilities, yet another lecture. But universally, no matter what you start with, you end up with this, if you look in the local rest frame of the plasma, and I think about just trying to read off the one particle distribution function, this is now in momentum space. This is the transverse momentum direction, the longitudinal along the beamline direction. I'll get cooling in the longitudinal direction, and so I get a squeezed distribution. Now, if there's any interactions, what will happen is the particles that are in this squeezed distribution will start scattering off of one another. This expansion actually slows down as a function of time, as you're going to see analytically. And the moment that the interaction rate between the particles in this little blob here gets higher than the expansion rate, it will turn around and start going back towards equilibrium. Now, whether you end up on the top of this blue band or the bottom depends on the transport coefficients in the core colloid plasma, which are a measure of its level of interactions with itself. If it's not interacting at all, you just go down here and you stay at longitudinal pressure 0 forever. If you have a very high shear viscosity, which would be sort of the weak coupling picture, you'll land down here. If it's the strong coupling picture, you land up here. So all of these measurements of shear viscosity are sort of telling you where you are on this curve. Yeah. Mm-hmm.
First question is, maybe it's better if I use a microphone.
Mm-hmm.
You have already partially answered maybe, but having the negative pressures could lead to some sort of instability, like hydrodynamization instability or something like that. And second question, suppose that you start from longitudinal transverse around 1, okay?
Yeah.
If then you go below 0, shouldn't this signal some shortcoming of your theoretical approach, or does it have also a physical interpretation?
Yeah, as you're going to see in some examples, even in the introductory slide, you have to be very careful here. So many people, and there's papers about it, which mention the fact that if I go negative, then I get some sort of instability to bubbles. But very frequently what they're doing is just pushing their theory beyond its limits, and they get a negative pressure and they don't know how to interpret it. Now in practice, actually there is a threshold, which is what is the pressure of the equivalent hadron gas. So the moment you get below the pressure of equivalent hadron gas, you can go into a hadron gas locally. And that can happen, but it's actually not at 0. It's like the vapor pressure, if you like, of a hadron gas. But yeah, just saying negative means instability, that's a myth. Yeah. Now, there is an instability down here, but that's related to some other weird physics called a Weibull instability. That's not this sort of bubble nucleation physics. Yeah.
The fact that when you're increasing in time, you have a decrease in shear viscosity, that's because of the superconductor.
Okay. Use the mic and switch on the mic.
Okay. So as time goes by, there's a decrease in shear viscosity.
Well, all I'm saying is you can either be on this part of the curve or you can be anywhere in here. What I'm saying is where you land here on the top part of this curve or the bottom depends on the shear viscosity. If you had very close to 0 shear viscosity, you would come up here and you would go back to nearly 1.
Okay.
Yeah, it's not that it's decreasing. I can hold the shear viscosity constant just as a theoretical exercise in my brain. And it will just ride one of these curves. And we're going to see this in some actual calculations. Yeah, so I can hold the shear viscosity constant. It's just where I land here depends on the shear viscosity, whether I'm on the top part of this band or the bottom. Is that clear?
Yeah. But I mean, I was wondering if, like, the fact that as the plasma evolves, it tends to hydrodynamization, then the number of free color charges.
Yeah. So so you're right. So what happens in practice is more complicated than my thought experiment, right? So if I plot the shear viscosity to entropy density ratio as a function of temperature, at around this pseudo-critical phase transition is where it has a minimum, and then it shoots up very rapidly as you go down in temperature. And so in practice, you'll sort of do a transverse through this curve where you go here, and then the shear viscosity gets large again, and then you fall out of equilibrium over here. In fact, the free streaming phase of late hadrons, they're out of equilibrium. They have some sort of fingerprint of the fact that this phase of the quark-gluon plasma, sort of passed near to equilibrium, but by the time they're out here, it's no longer an equilibrium gas. I mean, it fell out of equilibrium because they're not interacting with one another anymore. You don't keep them in a box. Yeah. So it's out of equilibrium, in equilibrium, then out of equilibrium again. And the thing that we really count on is that at this moment of freeze out, they're sort of close to equilibrium. That, that's the only thing that we kind of require. And even that can be slid a little bit. Any other questions? They're good questions. And I don't mind not covering material. Sorry, yeah, let's pass it back.
So you have the circle on the figure, the next figure.
This?
Yeah, this one.
Yeah, this is just to show that you go back closer to isotropy, but you're not fully isotropic here. Yeah, so it's not quite a circle. I was careful to make it slightly squished. Now, if it was a perfect circle, then this line would be sitting up here at 1. Yeah. So as I move down here, I get more squished, and as I move up here, I get a circle in momentum space. Is that clear?
A perfect circle means what? Thermal?
It means thermal isotropic distribution, that I have as much momentum in any direction. I can look along the x, y, z direction. In a thermal system, I should have the same expectation value of px squared, py squared, and pz squared. By definition, that's thermal equilibrium.
Okay, so isotropic, that's why you use circle.
Yeah,
Okay.
yeah. So there's, in a kinetic theory language, there's two sort of thermal ways of thinking about thermalization. One, I have a kind of Boltzmann distribution, right? That if I plot things on a log scale as a function of momentum, I see some nice exponential distribution. That's related to the e to the minus Hamiltonian over t that Francesco was showing us earlier. But there's an additional requirement. Not only should they have some nice spectra that look exponential, if I do that spectra as a function of px, py, or pz, it should be exactly equal, right? And that's isotropy. So there's two kinds of requirements that are writing here. These are very good questions. Okay. So just why are you hearing these lectures? Why is this topic relevant at all? So I made this point in the introduction that the quark-gluon plasma seems to be highly momentum anisotropic in the local rest frame, particularly at early times. This also happens to be the case if you look out on the transverse edges, where not in the center of the collision, but as you move more towards the dilute regions, because there you might only have one or two nuclei colliding, nucleons colliding with one another. There's no way you're generating a quark-gluon plasma on the edge, right? It's only in the center-most hot region. Now, the surprise was that, before we understood this, people had been applying this viscous hydrodynamic stuff for a while, and it seemed to describe all the data. And I'm going to show you what describing all the data means in a couple of slides. And the whole question of why does this whole hydro thing work so well sort of became crystal clear. I put Heller and Spolinsky paper here from 2015, but it was actually, for me, a paper by Paul Chesler and Larry Yaffe from the University of Washington in 2006, which was predated this one by 9 years, in which they did this ADS-CFT calculation, and they found that, hydro applied, but it was out of equilibrium. I'm going to talk about now, instead of, we're trying to replace the word thermalization by something that's really hard to say. I can't never even say it right. Hydrodynamization. If I try to say it fast, I can't. We tried to replace it by hydronization, but people said that we couldn't do that. Said it was confusing. But I can't say that word, so I'll just point at it and say, that word. And what I'll do over the course of the lectures is show you how we understand this within hydro itself, and then also how do we understand it in kinetic theory. There's a couple of different ways in the literature where you can get the hydrodynamic equations of motion out of the equilibrium. One is based on symmetries and requirements like Francesco was showing you earlier, of requiring positivity of the divergence of the entropy current. or ADS CFT sort of stuff. I'm going to focus on kinetic theory because I only have limited time. Now I want to show you why we were also surprised and how well these sort of models can describe data. And I just want to quickly, you won't understand most of this, but by the end of the week, the hope is that you'll understand some of the terms here.
Can you go to the previous slide?
Yeah, no problem.
So I understood. That there is a momentum space anisotropy, but how does that imply that hydrodynamics is not happening?
It doesn't. Well, now it doesn't. But circa 2006, there was a sort of dogma in the field that said it had to be perfectly isotropic by 0.6 Fermi over C, or very close to isotropy for hydrodynamics to work. What's changed now is that we've seen that you can push hydro much farther away from equilibrium than we thought 17 years ago. But you're right, the one thing doesn't imply the other, but that was where we were stuck for quite some time. All right, so Francesco gave you a sort of flash introduction to hydro this morning. We have to specify some initial conditions on some hypersurface that includes like the energy density profile. I'll show you pictures of this. We also have to specify the non-equilibrium corrections, which get collected into a tensor called the viscous tensor, pi mu nu. It gets added to T mu nu as the non-equilibrium correction, and we also need to know for the initial conditions the full fluid flow velocity, and we need to know that on some 3D hypersurface. And then we have to, in practice, solve numerically, because they're too hard to solve analytically, some large set of coupled partial differential equations for the evolution of typically 14 degrees of freedom, which are, the number density, this might be the baryon, net baryon number density, all independent components of T mu nu, there are 10, as we learned this morning, and then the 3 independent components of the 3 velocity. So there's at least, 14 degrees of freedom floating around. We solve those partial differential equations. This is what they look like. In practice, they're a large set, and this is like the bulk viscous correction, this is the energy density, this is the pressure, this is a co-moving derivative of the floor velocity, and you can see they're complicated. I'm not going to derive this for you on the board, of course. This was derived originally by Denikal, Niemi, Molnar, and Rischke in Frankfurt circa 2005 or so, something like that, 7, I forget the precise year. And then there's a bunch of other stuff which you won't recognize. There's something called delta pi pi, and these are things called transport coefficients. Eta's flying around in here somewhere. There's eta, that's the shear viscosity, that's the bulk viscosity. Then there's these things called relaxation times floating around. Within any given theory that you start with, you can derive what are these transport coefficients. So if I tell you this is the quark-gluon plasma, go sit in your basement for 10 years, eventually you might be able to return numbers for all of these transport coefficients that are in these equations. But that doesn't change the fact that you still have to solve them numerically, right? So you have to specify initial conditions for all of these 14 variables, solve the coupled partial differential equations. But then it's not over. As Francesco pointed out, and I also mentioned in words, eventually you're going to get to a region where it's so dilute that you want to convert back into hadrons. And you actually don't do this at the phase transition temperature in practice. Actually, you do it lower than the phase transition temperature because hydro doesn't care what degrees of freedom you have. It could be quarks, it could be hadrons, it doesn't care. In fact, that's the beauty of hydro. And in fact, the benefit is that you can drive it into the hadron phase from the quark-gluon flight. And by the time we reach this freeze-out hypersurface, we believe that the fluid's already been reconverted into hadrons. And now all we have to do is sample the hadrons that are flying out. And that's accomplished through a sort of canonical formalism, which is called Cooper-Frye freeze-out, where I have some model for the one particle distribution function. That's my little squeezed ellipsoid that's not perfectly thermal. P mu is encoding the momentum of each of these particles as they fly on out of the hypersurface here. And then this is the integration measure over this hypersurface here. And then there's some degeneracy factor, which is counting, say the number of isospin degrees of freedom per pion and so on, that's sitting out front. But I compute some integral like this for the ith hadron, and then that tells me the full spectrum that will be produced experimentally. And then I can integrate this over whatever, if I integrate it over all D3P and divide by P naught, then I get the total number of particles that are produced for particle species I, but this is the fundamental thing that you compute in the end.
So you extract the hypersurface through that formula, or do you need it to calculate?
You have to determine this. Typically, it's determined numerically. And the way you do that, and there's different prescriptions, but usually in practice, you have to find an equal energy density surface. So that's what this surface here is. I found when was the energy density equal to the lattice equation of state with a temperature of 130 MeV. So you can then find a surface, and then you integrate the viscous corrected one particle distribution function on that hypersurface, and that tells you the number of particles produced. Now, people tried different things, isochronous, proper time, there's various different prescriptions, but this is the one that people frequently use. There's other ones, I won't. Now, the story isn't completely over. After you produce the hadrons that fly out here, you still have this hot hadron gas phase of the evolution. Some things can still decay down. They can collide and undergo inelastic collisions or elastic collisions. Both can happen. This is called feed down. So you have to take into account also this late time hadronic physics that's going on, which by most people's standards is, by quark-gluon and plasma standards is boring, but it's absolutely critical in order to get curves going through data. So there's a whole separate class of codes. URQMD, SMASH, Terminator, there's a whole slew of them out there that take care of this level of the physics. So you have some initial condition, run your hydro, get the QGB produced particles, then feed them to a hadronic cascade, and then you get the final spectrum and compare that to data. So it's a complicated multi-chain step, and you have to know how to do code in order to do it. Now, I'm going to show you how well it works in one case. So this is a hydro model called anisotropic hydrodynamics that I invented with a student in 2006. And then we turned it into a 3+1 dimensional code that we could then do all of this entire chain of simulation with. And what's plotted here is the transverse momentum. On the horizontal axis is the transverse momentum. On the vertical axis is simply experimentally the number of particles that you counted in your detector. Right? So you measure in this little window of PT, you count the number of pi pluses and pi minuses. Here you count the number of k pluses and k minuses and so on. And the experimental data points are there, and then the theory predictions are here. Now, they weren't exactly predictions because we had some fit parameters to play with, but we didn't have very many fit parameters in this particular paper. We only had the initial central temperature. That's if they had it exactly head on. Now, these ellipses are actually let me correct, these ellipses are the nuclei. So one is going into the board and one is coming out, and they're actually circles, right? So I have nucleus A, and it's going to collide with nucleus B, and they don't have to be the same size. And then there's some overlap regions. So this one was going into the board and out of the board, and this one was going into the board. A central collision is when their two centers exactly overlap, and as I separate them apart, this is called the impact parameter. Eventually they don't collide at all. So these different panels are just varying that impact parameter all the way down to what's called 40 or 50% centrality class, where they're almost not colliding at all. You keep going, there's just Now we expect the quark-gluon plasma to be generated here in the most central collisions where we have the most stuff interacting, and as we go out in this direction, eventually we should turn the quark-gluon plasma off, or at least should have a very short lifetime. And in this case, we just did the fit here in 0 to 5%, and we extracted the central temperature, this shear viscosity. We didn't do anything fancy. We said it's a constant because we didn't know better. So we said it's 2 times the lower bound. That's what this is encoding for. Pi eta over s is equal to 2. And then we also had to specify where we did the freeze out in temperature. So that's what this third parameter was. So once we did that, we could describe this spectrum pretty well, and then it described every centrality class after that. Yeah. I can.
So that function f, I'm sorry.
Yes.
That function f you can get from, how do you get that? From the hydro parameters?
Yeah, so you get it from the hydro parameters, and as we go through the board lectures and then finally wrap up on Friday, I'll show you explicit forms for the viscous corrected F. So there's a way to express the viscous correction in terms of the one particle distribution function. If the one particle distribution function is perfectly thermal, the viscous correction by definition is 0. But you can also invert this relationship and express the one particle distribution function in terms of the viscous correction. So it's an equilibrium distribution function plus some correction. And so there's a systematic way to figure out what this thing is. Yeah. And it involves the viscous corrections.
Yeah, so what's the difference between the anisotropic hydro and Israel?
Yeah, so I'm not going to explain everything. You're going to hear that in lecture 2 or 3, I don't remember. So actually that's the whole, is to tell you the difference between these two. It's, in summary, Israel Stewart assumes that you're near equilibrium, that you're near isotropy, and anisotropic hydrodynamic throws that assumption out. It says we don't have to be nearly isotropic. But you're going to learn, hopefully, if I get to it, what the precise difference is. Now, of course, I can get a lot of other observables out of this. I can now integrate over PT as well, and I can plot this now as a function of what's called rapidity. Now, rapidity is if I have 2 nuclei colliding, just a second. If I have 2 nuclei colliding in this direction, there's the transverse direction, which is perpendicular to the beam line. And then there's rapidity, which is this angle. Rapidity 0 is perfectly transverse. Rapidity of plus and minus infinity is going down or against the beam line. So this is now stuff that's shooting out in the beam line. This is stuff shooting the other way down the beam line. This is stuff shooting straight out perpendicular to the beam line. There was a question while I remike myself.
So from the previous slide, I'm wondering whether there is any particular reason why the theoretical field seems to be very consistent at central collisions, peripheral collisions. The fact that we sort of like keep the fit parameters at one centrality class and then apply it generally throughout all the centrality classes.
Yeah, so the basic model is that I'm always creating in this core, whatever this overlap here is, a quark-gluon plasma. Now, as you can see over here, we're starting to get some breakdown of the theory. It's not agreeing everywhere with the data. And this part is a high momentum tail that eventually will take over everything. There's a sort of low momentum part, which is the sort of thermal QGP part, but there's always hard collisions, and they won't have an exponential distribution. They have a power law distribution. The question is, when does this exponential give way to the power law? And if we get more and more peripheral, eventually you're not even making a quark-gluon plasma. You're just having hard scatterings between nucleons. You won't thermalize it. But yeah, so the reason that we can describe, let's say, out to 30, 40%, up to 1.5 GeV is that we're always creating a quark-gluon plasma here in the center. And we don't have to change the physics. Now, one thing I will note, although it looks, the scale is changing here. So this is 2,000 over here, and this is 200 pions over here. So there's a very non-trivial dependence on the centrality, which is just automatically predicted by hydro. And that's summarized here in this plot, where now what I'm looking at, this is just the number binned in now this angle, which is with respect to the beam line. And the top is central collision, the bottom is peripheral collision, and this, it seems to work very well, right? I'm not going to go through. Now, it doesn't just describe these numbers, like how many pions do you get, how many nucleons do you get of all different types. It also describes the space-time evolution of the quark-gluon plasma very well. So this is a different representation of our heavy ion collision. In a cartoon form, I had one coming out of the board, one going into the board. They collided, there's this elliptical deformation, and they pull out a tube of quark-gluon plasma between them. Now, because this side is shorter than this side, there's going to be a higher energy density gradient along the short side than on the long side. And early predictions, this is a plot from 23 years ago, were that if you had such a deformation, you would see that it expands more along the short side than the long side. It wants to shoot out this way. And you can quantify this in something called the elliptic flow. In fact, there's a bunch of different flows. The way that experimentalists define the flows is you have some collision like this, you put a detector that wraps 2 pi around it, and then you just measure all the particles as a function of azimuthal angle. Of course, it's a periodic function because it's a circle, and therefore I can always decompose it into a discrete Fourier series in terms of cosine phi, 2 phi, this is cosine 0 phi, 1 phi, 2 phi, 3 phi, and the coefficients in that Fourier discrete Fourier series are V1, V2, V3. This is the one that people were primarily interested in. There's lots of physics related to the rest of them, and I'll show you some stuff about V3. If you only had an idealized heavy ion collision, where it looked like this cartoon up here, you would primarily only generate V2, and there would be no V3 or V4. But in practice, a heavy ion collision looks nothing like this cartoon. The initial condition looks more like this. This is on one of those hyperbola. So a fixed proper time hyperbola, you have to sample the positions of the nuclei and you get some fluctuating initial condition. You have to run this code 1,000 times now, because every time you do the nucleus-nucleus collision, you get a different initial condition. And then because and we'll see some more pretty pictures of this later, because of these fluctuations in the position of the collision points, you can start inducing V3, V4, V5, V6, and so on. Yeah? Now, again, having only tuned those 3 parameters and not changing anything, you can make predictions from these hydro models for V2, even for specific particles. So this is pion, kaon, and proton. This is pion, kaon, and proton as a function of PT. And we can see that at some point it stops working. That's when you're transitioning out of this hydro regime. The momentum exchanges are too high. It's not really describable by hydro anymore. People argue over where exactly that threshold is, but we can see roughly with our eyes that it's somewhere between 1.5 and 2 GeV, but everything below there you seem to describe quite well just using this sort of fluid model. And now this is a result not from me, but from that former student, Bjorn Schenke, Charles Gale, and Sengyong Zhan from McGill in 2013. Using now fluctuating initial conditions, they could also get V2, V3, V4, V5. Now over here is central collision, over here is peripheral collision. And what's the difference between the left and the right? Oh, this was just 2 different ways of measuring V2, either with 2 particle correlations or event plane V2. Anyway, it has an amazing predictive power. And so then the questions around this time started being, why the heck does it work so well? Is the system really in thermal equilibrium? Well, we knew the answer to that was already no, because these codes had to include viscous corrections. If you did not include the viscous corrections, you did not describe this data. So we already knew that it wasn't thermalized in circa 2013, right? And you had to include them in order to describe this data. Now, an even further surprise emerged a few years later when people started analyzing not just lead-lead collisions, but say a P-lead collision or even PP collisions. And what they found was that you could also take the same hydrocode and describe the flow and also the spectra, which I don't show you here because I don't have enough time. You could describe all of that using the same code. Now you have to make a cut on the data in this case, and the cut in this case experimentally was what's called the number of tracks. It's simply the number of particles in their detector that they saw. If there was only 2 particles generated in the final state, probably it wasn't hydrodynamics, right? You just had 2 jets and that was it, right? So there was a kind of lower threshold above which you started to see collective behavior. And it seems to kick in at a very, very low number. You only needed like 100 tracks in the detector before you started seeing collective behavior. So this came as a surprise. And people were extremely surprised, like, why would it work in this case? Because if you look inside, and I'll show you what's going on inside these simulations, it's very far from equilibrium. It's never even near equilibrium. So this old picture just sort of started collapsing. All right, so how do we see that there may be some non-equilibrium deviations going on? By just examining the output of the codes, right? We run the code, it describes the data, and we're like, okay, now let's look inside the code and figure out what's going on. So I'm going to show you some slides that have lots of fluctuating initial conditions. So I wanted to show you what a fluctuating initial condition looks like. So this is in a particularly simple one, which is called the Monte Carlo Glauber model, where I imagine the nuclei are just bags of nucleon, and then I Monte Carlo sample which ones collide with one another. And I randomly distribute the nucleons in nucleus A and nucleus B, and then I randomly pick their collisions. That's the green and the blue. And the animation is over each sampling of this. Gabrielle?
The last result you showed for P-lead collisions, is this for one particular chain, or were there comparison between chains?
So this is using Bjorn Schenke, Chun Shen, Gabrielle Denicol's music code. I believe the URQMD afterburner. I don't remember the details from this paper, but yeah. It shouldn't depend on the chain. But I try to show other people's results so you don't think I'm, hoodwinking you. It's not just me that can put curves through the data. Other people can do it. Yeah.
Excuse me.
Yeah.
Which is the parameter that you use to quantify how far you are from equilibrium?
That's we're getting there. I have to walk you through it. All right. So what I'm going to show you is a particular instance of this fluctuating initial condition. Each of them each time I sample it, it looks a little bit different, right? So this is what one might look like. So this is the initial condition, and what the different columns are if you assume different levels of sophistication in your hydrodynamic simulation. The left is, I assume that it's in perfect thermal equilibrium the entire time. I won't describe the data with this. The other is I assume there's only shear viscosity, and the other is I add in the bulk viscosity. Now you can, in large part, do a very good job with just the middle. To get everything right, you need to go all the way to the right. The top row shows you the initial condition, which is the same for all 3 cases, and then the bottom shows you what they look like evolved 2 Fermi over C forward in time. So this is on the next hypersurface up. Is that clear? So going back to Francesco's picture, T here and Z here, and I can't draw the transverse plane. You'll forgive me. So we start here at, I think it was 0.5 Fermi over C with some fluctuating initial condition, and then we evolve it forward in proper time to the next hypersurface, and that's the bottom set of plots down there. Good. If you move from the left to the right, you can see that, by your eye, it gets more smoothed out. Well, that's just the viscosity. Viscosity smooths things out. You can't really tell a difference between these two unless you have really, really good eyes. trust me, there's a small difference.
Wouldn't that difference, I think your slide answered my question, I'm sorry.
Will it continue? Well, yeah, so let's go forward in time. So now we're at 6 Fermi over C, and now on the bottom we're at 10. And now I can start to see a difference between these things. And maybe this would result in some measurable impact that I could pick out of the experiment. The other thing, now you see some really interesting features over here. You see shock waves. That's because there was no there's no viscosity. So you get all these sort of shock waves, and the existence of these shock waves is what throws off V2 in ideal hydro case. You have a much higher elliptic flows because of the shock waves. The viscosity smooths it all out. Yeah. So because of this mass over here, you don't describe any data. Questions before I go to the next slide? I'm going to sip some water. Good. All right. So then there was a question, how do we know that any of this makes sense internally, self-consistently? How do we measure how far from equilibrium we are? Well, in hydrodynamics, we use two numbers traditionally, and we still use them since I guess the 19th century. They've been upgraded to relativistic versions, but there's still two numbers. One is called the Knudsen number, and it basically measures the gradients now in the system. Now, if there were no gradients, let's say the temperature in the room was completely constant everywhere, it would stay in equilibrium, right? There would be nothing interesting going on. No particles would move around. Nothing interesting would happen. That would be the limit of 0 Knudsen number. There's no gradients. So this Knudsen number measures gradients. Now, formally, it's a ratio between some microscopic relaxation time and the expansion rate of the plasma. And as I told you, the expansion rate of the plasma increases as I go further back in time. So over here, it's expanding like mad, and as I go forward in time, it starts to decrease. And as we're going to see, you can write this as this microscopic relaxation time, which is called tau pi for the shear relaxation time. There's also a tau capital pi for the bulk, but let's focus on shear for a moment. And then something called theta, which I'll define on the board in a few slides. It's the forward divergence of the fluid flow. If there was no fluid flow anywhere, this thing is 0. That was my homogeneous case. There's nothing flowing left or right or doing anything interesting. But in the very early time of the heavy ion collision, this thing is big. And turns out theta goes like 1 over the proper time. So the further I go back to the hypersurfaces to earlier and earlier time, the bigger theta gets. And eventually this Knudsen number gets huge. So if you go and you look in like the Groot book, which was recommended earlier, it will tell you when the Knudsen number is large, hydro doesn't work. You're not supposed to use it. So we can use this number to sort of monitor, how far is our system being driven out of equilibrium. Now, not how far is it out of equilibrium, it's sort of the gradients that will drive it out of equilibrium eventually. The number that quantifies how far it is from equilibrium at that moment in time is called the inverse Reynolds number. And it's defined, where's that pointer coming from? I don't know where that pointer is coming from. I will ignore it. Oops, don't do that. It's defined, and we're going to introduce this on the board. We saw it on Francesco's slide. There was some tensor, which is this is the viscous correction, in this case, the shear viscous correction to the energy density. The bigger this thing is, the farther you are from equilibrium. If pi mu nu is 0, you're in equilibrium. It's a tensor, so we need to define some Lorentz invariant way. So we just take the full contraction of pi mu nu with pi mu nu. This thing turns out to be correcting the pressures. So after taking a square root and divide it by the isotropic equilibrium pressure, this gives us our measure of how far from equilibrium we are. If this number is bigger than 1, then the viscous corrections are bigger than the equilibrium pressure. And you should be worried. Likewise, you can define a similar thing with the bulk. It's a scalar, luckily, and you just take the magnitude of it and divide by this. And very frequently, You see people talking about cavitation here when this inverse Reynolds number gets bigger than 1. Sometimes pi can even be negative. It can drive the pressure negative, and people say the thing cavitates then. But typically, it's when their theory is breaking down. Yeah.
No, it's up to you if you want to make a break or it's up to you.
No, let's keep going. I'm going to make it to the end of the slides, and then we'll take a break. Is that okay? I know, unless somebody has to pee urgently. Okay. I'll take that as a whimpering yes. Okay. I'll move faster. So you can plot these things. Same simulations that I showed before. Now what I'm doing is just taking a slice in the x direction. Right? So I'm just taking along y is equal to 0, taking a slice and now showing it to you as a function of proper time. And the color coding on the left is showing you the shear inverse Reynolds number, and on the right, the bulk inverse Reynolds number. And what we see, anywhere it's red or even black down here, or maybe even, let's say, green, is where you're being pushed very far from equilibrium. And as we can see out here in the periphery, it's always out of equilibrium. That's not surprising. But in the interior, we see that there's a time scale, roughly 2 Fermi over C, after which everything starts to get nice and blue. Yes? Yeah. Yeah, so it can get even worse than this, yes. That's true. This is with Monte Carlo Glauber initial conditions, yeah. So with Glauber initial condition, yeah, so with Glasma, you already have a very low longitudinal pressure to begin with. In the case, but as we're going to see in a couple of slides, what you start the longitudinal pressure with gets wiped out after a very quick amount of time, turns out. So the reason I titled this slide, "Don't Worry, Be Happy," is because that by the time we hit this, temperature, the phase transition, everything's blue. That's Francesco's, freeze-out hypersurface. And that's the point in time where I say that, yeah, it looks good. You're near equilibrium now. Now, of course, here at 0.1 Fermi over C, I don't think or 1 Fermi over C, nobody would say it's in equilibrium. And even if you started it in equilibrium, which Monte Carlo Glauber does, it doesn't remain there. Now on the right shows you the same thing with the bulk. The reason that you see a shaded region around, we put the phase transition, well, the peak in the bulk viscosity, there's a peak in it as a function of temperature at 200 MeV for this example. That's related to a peak in the bulk viscosity. And if your freeze out point gets too close to where the peak in the bulk viscosity is, you can also have problems here. That's a different story. Now, this one I titled "Don't Be Happy, Worry." And this is a P-lead collision. It wasn't done by me, it was done by Harry Niemi, who's in Jyväskylä, and Gabriel Denical, who used to be in Frankfurt and is now in Niterói in Brazil. And they looked at various different prescriptions for 8 over S. It was a constant, it was varying. I think this one has the true temperature-dependent shear viscosity model in there. And as a result, and now instead of the inverse Reynolds number, they plotted the Knudsen number, but they're correlated. Whenever the Knudsen number is big, it's immediately followed by inverse Reynolds numbers being big. So down here, because of this large shear viscosity at early times, it's already red. You should not be happy. And then even when this is how they varied the freeze-out hypersurface in this case, it was basically always in the not good region. But the amazing thing was they were able to describe data. So everybody started scratching their heads. What the heck is going on here? This was 2014. All right. And these large deviations were due mainly to this large pressure anisotropy. All right, so that led us to a bunch of questions. Can standard viscous hydrodynamics treatments can they describe very early time dynamics reliably? Are they going to break down? Typically, they're done in a sort of power counting linearization around equilibrium where I sort of truncate the series at some point. Of course, any truncation is like a Taylor series. It can break down at some point. So people started asking, well, how far can I push it back in time? And if there are these large non-equilibrium corrections at time, will the final results be sensitive to them? So does it depend on the initial condition? Because I don't stay in thermal equilibrium all the time. Will there be large dependence on the initial conditions? And finally, just from a sort of numerical point of view, if I make a mistake at early times, does it propagate through the whole simulation and destroy everything at late times? These are the questions that we were and still are interested in. And now comes the actual topic of the lectures. So, and I'll just leave in a few slides, I promise. So this was the surprise that came out, let's say 2015-ish. And people started noticing the following. So now I'm going to plot the same variable that I was showing you in the cartoon, PL over PT, as a function of proper time. If it's perfectly isotropic, it's 1, and then all the different lines are starting with different initial conditions. Actually, this one started way up there out of the room on the second floor somewhere. Very prolate distribution. And the top and the bottom panels are changing eta over S from roughly 2 times the lower bound to roughly 5 times the lower bound. And then this is what happens if I put those two on top of one another. And you start to see my cartoon emerge, right? That I have some large band of things. The smaller the shear viscosity is, I emerge over here. The larger it is, I'm down here. And so if I were to make a cartoon out of this, it would start to look like the cartoon that I showed you before. And we already see some hints of universal behavior, right? All of these curves seem to sort of pile up in one place here, irrespective of the initial condition. And likewise, down here, all of these curves seem to pile up in one place down here, irrespective of the initial condition. But the real surprise came when people started making this plot. Instead of plotting it as a function of proper time, you plot it as a function of the rescaled time, where rescaled, in this case, I take the proper time of the simulation and I rescale it by the local relaxation time. Now, in this picture that I'm showing you here, the local relaxation time was 5 times eta over S, that's what eta bar is, divided by T. And eta was a constant, but you can even do it with time-dependent shear viscosities. And what you find is both of those runs collapse down to this. And you get a universal curve that's going here. And if you stare at it long enough, you can convince yourself there might be a universal curve that extends all the way back here. And irrespective of the initial conditions, I collapse onto that universal curve. And that's what people call the attractor. And and this starts to look a lot like my cartoon, but it's even better than the cartoon because it's now, there is something universal going on out here. It's not a broad band anymore. We've even scaled out the eta over S dependence. And what we see is that irrespective, we still have a very large momentum anisotropy persisting over here. Now, yes, go ahead. Yeah, so this came from hydrodynamics equations. In this case, it was anisotropic hydrodynamics, just solving a set of couple partial differential equations. This was in 1 dimensions with Bjorken expansion. Yeah, so this is a simplified case. So you just have the longitudinal expansion. You don't have any transverse expansion. Now, if you start including the transverse expansion, it does not collapse down to these lines. It does something different. It collapses to the lines and then they go apart at late times because the system falls back out of equilibrium because of the transverse expansion. But there is what we were always primarily interested in is what's going on in this first 5 Fermi over C. And there you can roughly ignore the transverse expansion. So this is just that one-dimensionally expanding tube and even more assumptions, conformal, boost invariant, and then it collapses perfectly.
But this picture would be true for very high energy.
For very high energy densities, or?
No, very high collision energy.
Yeah.
What collision energy in this picture?
Everything, yeah. Actually, it would be even more true for very high collision energies because as you go to higher and higher collision energies, you get more and more conformal and more boost invariant. So this becomes the high energy limit.
Then your questions will be different at lower energy. At lower energies, we have like more transverse expansion compared to the conventional.
Now, in the high energy limit, you're still expanding at the speed of light, and the interactions are slower. You get to this boost invariant limit, and you're in the T goes to infinity, so you're in the quark gluon plasma conformal limit. So, at lower collision energies, all of this gets blown. Yeah, you have to be very careful with this. At lower collision energies, this doesn't work. Higher, yes. Lower, no.
But the question would still be validated that how hydrodynamization at lower energies. I mean, would that question be valid?
Yeah, it's a valid question. You should write a paper about it. I agree. No, it's an open question. Nobody really knows. I mean, so the latest papers are, and which if I ever get there, are about breaking even basic symmetries, like going to 1 + 1 or 2 + 1 instead of this, or breaking the conformal symmetry. Does it still survive? And in this case, it's a sort of strict thing that it collapses to a line, but in practice, you don't really need it to collapse to a line. You just need to be a very tight band over here, and then you have a lot of predictive power, even without it being a unique line, mathematically speaking. So this is those same things, now with some more information added to the plot. So this is the actual attractor curve that they're converging to. I'm varying the initial conditions. And then I've tried to put the time scales here for you. I initialized at 0.25 Fermi over C with a temperature of 500 MeV. And then I see by roughly 1.3 Fermi over C in these units that it's collapsed to this universal curve. And this green dash curve is Navier-Stokes hydrodynamics, otherwise known as first order hydrodynamics. And we can see that it fails to describe reality at some point. And in fact, it goes negative, and we'll understand why it goes negative in the course of the lectures. All right, so I'm going to finish with this slide, and then we'll take a break. So this is a paper from Paul Ramachka, circa 2017, where it's a different variable that he's plotting here. It's not PL over PT, but it's sort of related to it. It's the upside down version of it. But the black curve is this attractor, and the three different panels are showing you hydro in some framework. I'm not going to try to name all the names there. This was an exact solution to the Boltzmann equation that I made with some collaborators in Krakow, and this is using ADS-CFT. Now there's some qualitative difference over here where you see oscillations. So these are sort of underdamped modes, and these can be understood from analyzing the quasi-normal modes of an extra-dimensional black hole. So people know why there was oscillations in this case and why they disappear when you go into kinetic theory and there's no oscillations. But the basic fact is that after some short amount of time in this rescaled time here, you collapse down and you're described by hydrodynamics. And your sensitivity to the initial conditions in terms of what the exact pressure anisotropy was to begin with just go away. All right, I think that's a good place to break. So what I'm going to try to do next, after we come back from the break, is start over from scratch. I'm not going to show you any more plots. So I'm going to go to the board, and we're going to start by deriving ideal hydrodynamics. And then we're going to go one step forward. I won't try to derive the full thing in the end. All the notes are online, so if you think that you can skip it, go ahead. But, I prefer if you showed up. Thank you.